Hello, hello. Rational root theorem is what we are going to use to find all possible rational roots for a polynomial. So normally we've been just using synthetic division to see what's left over, or using long division to see what's left over. This is going to give us options to factor this polynomial. So the rational root theorem says that I can find possible rational roots at p over q, where p is a factor of the constant and q is a factor of the leading coefficient. So we want to start off with plus or minus, and this is how I like to organize. So first step is to list the factors of the constant. The constant is the number at the end that has no variables, or that has degree 0. So I'm going to list all the factors of 6. The factors of 6 are 1, 2, 3, and 6, because 1 times 6 is 6, and 2 times 3 is 6. Step 2 is to list all of the factors of the leading coefficient. So the leading coefficient is the number that leads the pack. So here, the leading coefficient is 2. It's in front of the term with the highest degree in my polynomial. The only factors of 2 are 1 times 2. So when we list those factors here, we have our p over q. Now I want to go ahead and organize those fractions, those possible rational roots, and I want to simplify anything I might see. So I'm going to do 1 over 1, which is 1, 1 over 2, which is 1/2, and then I'm going to do that with each p over each q. So 2 over 1 is just 2, 2 over 2 is 1, I've already written that, so I don't need to write it again. 3 over 1 is 3, 3 over 2 is 3 over 2, and the last 6 over 1 is 6, and then 6 over 2 is 3. I already have 3, so I don't need to write it again. Now that we have all the possible rational roots, we're going to use synthetic division to test all of those roots so that we can find factors. Our goal is to factor this polynomial. So I'm going to test out -1 first, and if I don't get a 0 for a remainder, then I'm going to keep trying. So remember, when you use synthetic division, you're using the coefficients. You're listing them in order from largest degree to smallest degree, making sure to fill in any missing terms with zeros. Bring down that 2. The lead coefficient always comes down, and then we multiply, answer, add down. -1 times 2 is -2. Add down, you get -11. -1 times -11 is +11. Add down, you get 18. -1 times 18 is -18. And when you add down, you get -12. So because I didn't get 0 as a remainder, -1 is not one of my x-intercepts. So I need to move on and try another one. So here I'm going to test out +1 and use synthetic division with those same exact coefficients from the original polynomial. As I test this +1, I do end up getting a remainder that is not 0. So now I need to test the next one in the group. So I'm going to go ahead and try out -1/2 and see if that will give me 0 for a remainder. It is very possible to test every single one of your possible rational roots and not get a 0 for a remainder. So you might not have any real rational roots. But with this -1/2 that we test, we do end up getting 0 for a remainder, which means that -1/2 is one of our zeros. So here's the tricky part. We need to take that -1/2 and change it back into a factor if we're trying to write this in factored form. So we know that we have 2x squared minus 10x plus 12 left over. We got to figure out what that factor is in that little box. So remember that that comes from setting a divisor equal to 0. So we're going to work backwards from x equals -1/2 to eventually get something that says equals 0. So I'm going to multiply by 2 to get rid of that denominator on both sides, and I'll get 2x equals -1. I'll add 1 to both sides, and I'll end up with 2x plus 1 equals 0. That means that that 2x plus 1 is one of the factors. To continue factoring this, you could continue to use the rational root theorem again with your new last term and your new lead coefficient, or you could try to factor using the methods that we know how to factor. So here I'm using the method that I know how to factor because it's shorter than going through the rational root theorem again. So I take out a GCF of 2, and then I'm left with x squared minus 5x plus 6. That plus sign at the end tells me that my signs are the same, and the minus sign in the middle tells me that both of them are negative. They have to multiply together to give me positive 6, but add together to give me negative 5. So I end up with x minus 2, x minus 3. I can now write that as a full factored form. I put my 2 in the front, my 2x plus 1, x minus 2, and x minus 3. That is the factored form of this original polynomial. Now that we have all of our factors, we'll be able to sketch a graph of this function. We know the end behavior because we can see that this is degree 3 and it has a positive leading coefficient. So that means that the end behavior is going to go down on the left and up on the right. We have all of our x-intercepts. Those come from setting each one of those factors equal to 0. So 2x plus 1, if you set that equal to 0, you would get negative 1/2. X minus 2, if you set that equal to 0, you would get 2, and x minus 3 would give you 3. So I can sketch a graph of this function by first plotting my x-intercepts on the graph. I also know my end behavior goes up on the right and down on the left. I know that all 3 of these x-intercepts have multiplicity 1 because their factor only appears once. So I know that all of those x-intercepts are going to pass through the graph. I can also find my y-intercept by substituting 0 in for x. If you plug in 0 for x in any polynomial, the only thing that's going to be left is the constant. So you could think of your y-intercept as 0, whatever the constant is. All of those values are going to pass through the x-axis. So here's my graph. The point of learning all of this is so that you can eventually find all the factors of a polynomial and be able to sketch a graph of it. So I want you to try this one on your own. First, I just want you to find all the possible rational roots, p over q. So the factors of the constant over the factors of the leading coefficient, and then you want to clean those up. Go ahead and pause the video here. Try this, come back when you're done to check. All right, so we've got our possible rational roots listed here, 1, 3, 5, and 15. Those are positive and negative values there. So now's when we want to go on a little treasure hunt. We want to start testing those possible rational roots using synthetic division with the coefficients from that original polynomial, so 1, -3, -13, and 15. I like to start from the smallest to the biggest, so I'm starting with -1. You'll see that I don't get a remainder of 0. I get a remainder of 24. So I have to continue to test these possible rational roots until I find one that has a 0 remainder. So here I'm going to attempt to use 1. I'm going to use those same coefficients from that original function, 1, -3, -13, and 15. And my goal here is to try to find a 0 remainder. If I don't find a 0 remainder, I can test -3, +3, -5, +5, -15, +15. So from here, I want you to try to find the rest of those zeros. All right, so luckily with 1, we were able to find 0 as a remainder, so we could write that as a factor. We want to write that as x minus 1. And then the rest of those coefficients will give us our second polynomial. We can then try to factor that x squared minus 2x minus 15. Here's a hint. You're going to use your possible rational roots for the rest of your factors if that second polynomial is factorable. So we can also look at the end behavior here because we do know that the degree of the function is 3. So we know that it's got opposite end behavior. It's going down on the left and up on the right. We know that we have x-intercepts at 1, 5, and -3 by setting all of those factors equal to 0. So we can sketch a picture of this graph. Each one of those intercepts has multiplicity 1 because they only show up one time. So when I plot those points, they are going to pass through those x-intercepts. So I'm making sure it goes down on the left and up on the right, and then it passes through each of those x-intercepts. So I want you to try this one on your own. Go ahead and find those possible rational roots and start testing all of those possible rational roots in your synthetic division and hunt for those 0 remainders. Pause it here, try it, come back when you're done. So here I did try -1 first, and I got a remainder of 0, which left me with this 4-term polynomial that I could factor by grouping. And then I was left with a difference of squares, which factors again. So I was able to continue to factor this. This was just lucky. I just happened to pick one of those x-intercepts first. Remember that math is a building block. So if you do not remember how to factor by grouping or how to factor difference of squares, you're going to have to look that up on your own time. So here we can find our x-intercepts by setting those factors equal to 0. We can plot those x-intercepts. We can identify the end behavior from the degree and the leading coefficient. And then we know that each one has multiplicity 1. So it's going to pass through the x-axis. And we get this nice like W-shaped graph. So that's about it. Practice makes perfect. So practice these on your own time, and we'll see you next time.